In this video, I'm going to teach you the basics of microtonality. So that we can understand what's going on, let's start with a basic overview of how sound waves work to create music. Sound travels at a speed of about 1100 feet per second through the air. The simplest sound waves are sine waves, which look like this. They are also called cosine waves, but we will just refer to them as sine waves for now. All sound waves that you hear can be made up of multiple sine waves. These sine waves are the purest forms of notes. Now, when you hear multiple notes, they're all coming at you at the same speed at about 1100 feet per second. So how can you distinguish between different notes? It's because they have different wavelengths and thus different frequencies. Let's go over what these two terms mean. If we look at a sine wave, we can see that it repeats. The wavelength of a sine wave is the length per cycle, the distance it travels before it repeats. We can measure the wavelength of a sine wave by measuring the distance from crest to crest, the highest points, or from trough to trough, the lowest points of the wave. Both of these methods measure the wavelength of a sine wave. Frequency is the number of times we hear the cycle per unit of time, which is measured in number of cycles per second, known as hertz. So then we can calculate the frequency of a note by dividing the speed of sound by the wavelength. Let's do an example. If we have a wave with a wavelength of 10 feet, what is the frequency? Again, the speed of sound is about 1100 feet per second. So 1100 divided by 10 will give us a frequency of 110 cycles per second, or 110 hertz. Let's look at the general formula. F equals V over lambda, where F is the frequency of the note in hertz, V is the velocity of sound, and lambda is the wavelength. We can see from the formula that the frequency of a note is inversely proportional to its wavelength. So the longer the wavelength, the lower the frequency, and the shorter the wavelength, the higher the frequency. Frequency is what determines how high or low a note is. The lower the frequency, the lower the note, and the higher the frequency, the higher the note. This means that longer sine waves will sound lower, and shorter sound waves will sound higher. So now that we understand how to measure frequencies, let's move on to just intonation. Just intonation, or JI for short, is the tuning of musical intervals as whole number ratios of frequencies. Intervals with simpler ratios will sound more consonant. For example, if we take two notes with frequencies of 440 Hz and 880 Hz, these two notes have a frequency ratio of 2 to 1, since the higher note is exactly twice the frequency of the lower note. Let's listen to these notes. Notice how blended the notes sound when played together. Again, this is because the ratio of the frequencies is a simple one, specifically a 2 to 1 ratio. This can also be explained visually. When we look at the sine waves of the two notes, we can see that in the time it takes the 440 Hz wave to complete one cycle, which is about 2.5 milliseconds, the 880 Hz wave completes two cycles. What that means is that we are going to hear the same compound wave repeated every 2.5 milliseconds. That might sound a little confusing, so let's look at what happens when we combine these two waves. This is what it looks like when we hear the notes played together. Notice that the compound wave repeats every 2.5 milliseconds, just like each of the individual sine waves above. The 880 Hz wave completes two cycles, but still, both complete a whole number of cycles after 2.5 milliseconds. Again, because the compound wave forms a repeating pattern every 2.5 milliseconds, that means that 440 Hz and 880 Hz form a consonant interval. This 2-to-1 interval is called an octave, and is in fact the most consonant interval after the unison, which would just be two identical notes played together. The octave should instead be called a diatave, since the ratio is 2-to-1, but because of the traditional major scale that we all know, we call it an octave. Now, if you look at the 440 Hz and 880 Hz waves, you'll notice that some of the crests line up. But what if they didn't? What if, say, we shifted the 880 Hz wave to the right? What will happen to the compound wave? Well, with regards to just intonation, you don't have to worry so much about this aspect of waves. The position of the wave is called the phase of the wave, and I've included an interactive graph in the description of the video if you're curious about what would happen if we shifted the phase of one of the waves. The important thing to know for now is that if we shift one of the waves, the resulting compound wave would have a different shape, but would still possess a repeating pattern every 2.5 milliseconds. Let's look at another consonant interval before we move on to a dissonant one. This time I've zoomed out a little bit so that we'll be able to see the period of the compound wave. The frequencies of these two sine waves are 440 Hz and 1100 Hz, respectively. Note that this time the higher note's frequency is not an exact multiple of the lower note's frequency. However, these two notes played together will still sound consonant because 1100 over 440 reduces to 5 over 2. This means that the 1100 Hz wave will complete 5 cycles in the time that it takes the 440 Hz wave to complete 2 cycles. Both will take 5 milliseconds. So that means we know that the compound wave will repeat every 5 milliseconds as well. Let's now listen to the notes one by one and then together. The interval isn't quite as consonant as the octave, and we can tell visually as well, as we can see that the compound wave is more complex than the one for the octave. However, it's still extremely blended and consonant. The compound wave still repeats predictably, as we can see. Now, let's look at a dissonant interval. What if we combined a 440 Hz wave with a 622 Hz wave? 622 over 440 reduces to 311 over 220. This ratio is so large that we won't be able to make any meaningful sense of a repeating compound wave. Let's look at what the compound wave would look like. Can you tell where it repeats? Well, it does, but I haven't zoomed out enough. It would take a whopping 500 milliseconds before completing its cycle. To put that into perspective, the lowest note human beings can hear, which is around 20 Hz, completes its cycle in 50 milliseconds. So even though this compound wave here repeats, the human ear won't be able to hear this musically, but rather hear a 2 Hz beating, if anything. Let's again listen to the notes one by one and then together. As you can hear, the notes sound quite dissonant when played together. That's not to say this is an unusable interval. These two notes could be interpreted as A and E flat, which are both part of an F7 chord, or A and D sharp, which are both part of a B7 chord. However, as you may know, dominant 7 chords like these generally resolve to other chords with more consonant and stable intervals. These intervals that we saw and listened to earlier are more musical to the ears. To reiterate, intervals with simpler ratios will sound more consonant. So the goal of most tuning systems is to approximate just intervals well, with priority skewed towards simpler just intervals. I said approximate because even complex intervals that are very close to simple ones will be heard by the ear as a slightly out of tune simple interval. For example, 881 Hz and 440 Hz may seem like a dissonant interval as the ratio is 881 to 440, but this ratio is about 2.002 to 1, so the ear will hear it as a slightly out of tune 2 to 1 octave. In fact, it's so close that most people won't even be able to tell that such an interval is an out of tune octave. Now, you might wonder, what's the big deal? If we want things to sound consonant, why not use JI and tune everything to simple intervals? There are several articles and videos on why just intonation is impractical, but in summary, the problem with just intonation has to do with modulation, or key changes. For example, even if we weren't demanding much, we would run into problems with just intonation. Let's say we wanted to play the two simplest intervals above and below every note, 2 to 1 and 3 to 1. These are known as the octave and the 12th, respectively. Again, however, they are named based on the major scale that we know and not on the ratio of the interval. But even with just two intervals above and below every note, we would create an infinite amount of notes, even between one octave. Let's start with 440 Hz and see what happens when we start generating new notes. If we go up one octave, we multiply by 2, giving us 880 Hz. If we go up a twelfth from 440 Hz, we multiply by 3, giving us 1320 Hz. I've made 440 Hz and 880 Hz in bold so that we can see more clearly how many notes we have in an octave. The new note that is added each time will be in red. What we'll do from here is multiply the note's frequency by 3 whenever we're between the range of 440 Hz and 880 Hz to give us a new note, and then divide by 2 once or twice to give us another note in between 440 Hz and 880 Hz. In this case, we're outside the range, so we'll divide 1320 Hz by 2 to give us 660 Hz. That's inside the range, so we multiply by 3 and get 1980 Hz. Let's divide by 2 to get 990 Hz. This is still outside the octave, so we'll divide by 2 and get 495 Hz. Now we'll multiply by 3 to get 1485 Hz. Dividing by 2 gives us 742.5 Hz. Now multiplying by 3 yields 2227.5 Hz. So we divide by 2, giving us 1113.75 Hz. This is still outside the octave, so we divide by 2 again, resulting in 556.875 Hz. Multiplying by 3 brings us to 1670.625 Hz. And we can repeat this process, multiplying by 3 if we're inside the 440 Hz to 880 Hz range, and then dividing by 2 once or twice, whichever will take us back inside the range. You can see two problems here. First, this process never stops. We will always be adding new notes. Second, each new note added will produce a more complicated interval when combined with 440 Hz. For example, to get to the 1879.453125 Hz, we had to multiply 440 Hz by 3 7 times and divide by 2 9 times. That means that the ratio between these two notes is a whopping 2187 to 512. We could combat these two problems by stopping at an earlier point, but either way, the music you could play in one key could not be played in all of the other keys. To accomplish this, we must use an equal temperament. Alright, we've made it to equal temperament. Before we learn what an equal temperament is, let's learn about what an equal temperament is not. If we have the notes 440 Hz, 550 Hz, 660 Hz, 770 Hz, and 880 Hz, these notes are not equally spaced out. This is because the interval between notes is based on the ratios of the frequencies, not on the differences. An example of equal intervals is the interval from 220 Hz to 440 Hz, and the interval from 440 Hz to 880 Hz. Since 440 divided by 220 is the same as 880 divided by 440, both intervals are equal. And this is what we want from an equal temperament. From one note to the very next, the interval should always be the same. Of course, if we went straight from 220 Hz to 440 Hz to 880 Hz, the gaps would be too big. Imagine only having octaves for music. We'd be very limited in the music we could create. So we need smaller intervals. How can we best approximate just intonation with equal temperament? Since just intonation consists of whole number ratios, we want to approximate these ratios, again, prioritizing the simpler ones. In general, the smaller the interval between adjacent notes in an equal temperament, the more accurately just intervals can be approximated. However, having more notes makes instruments more difficult to play. So we need to find a good compromise between approximation of just intonation and playability. There are mathematical methods to determine such equal temperaments, though these are quite complex, so we won't cover it in this video. There's a link in the description though, if you want to learn more. For now, just know that most of these equal temperaments tune the octave very accurately, and so for simplicity's sake, most musicians tend to use pure octaves, tuning the 2-to-1 interval perfectly. Indeed, the most common tuning system used today is based on an exact 2-to-1 ratio. Let's analyze this. Modern music uses what we call 12-tone equal temperament, or 12 EDO, which stands for 12 equal divisions of the octave. This is because 12 EDO does a decent job of approximating simple intervals involving multiples of 2, 3, 5, and 7, the first 4 primes. We'll take a look at one octave of a piano and see how this is done. To get from the A on the left to the A on the right, we need to go up 12 equally spaced intervals. In other words, we need to multiply by the same interval 12 times. Let's call this interval r. Then multiplying by r 12 times is the same as multiplying by 2. That means r to the power of 12 equals 2. So solving for r gives us r equals 2 to the power of 1 over 12, or the 12th root of 2. This is then the interval between two consecutive notes in 12 EDO. We will now look at other intervals, but before we do that, I will introduce a new term. A degree is the smallest interval in an equal temperament. In 12 EDO, as we have just shown, the degree is 2 to the power of 1 over 12. An example of such an interval in 12 EDO is the interval from E to F. 2 degrees would then be 2 to the power of 2 over 12. 3 would be 2 to the power of 3 over 12, and so on. 12 degrees of 12 EDO is 2 to the power of 12 over 12, which is equal to 2, and so we are back to the octave. Let's now look at a few intervals smaller than an octave that use the first 4 primes and see how well 12 EDO approximates them. In column 1, we have a few JI intervals. In column 2, we have the closest approximation of each just interval in 12 EDO. Column 3 represents the decimal approximation of the just interval, and column 4 represents the decimal approximation of the 12 EDO interval. The first thing to mention here is, notice how 5 over 4 and 9 over 7 are both approximated by the same interval in 12 EDO. The same is true for 7 over 4 and 9 over 5. This means that 12 EDO tempers out 36 over 35, which is the interval between either of these two pairs of intervals. If you're not sure what that means, don't worry. I'll go over that in part 2. I just wanted to mention here that EDOs will sometimes map 2 or more JI intervals to the same thing. Let's now look at columns 3 and 4 to see how well 12 EDO approximates these just intervals. The closer the 12 EDO approximation is to the just interval, the better. Remember, since we hear intervals on a logarithmic scale, we have to divide one interval by the other to know how close they are. The closer the ratio is to 1, the closer the intervals. However, it's hard to see how close these intervals are in columns 3 and 4, so I'm going to introduce a new way of measuring these intervals, which is much easier for comparison's sake. Since intervals are heard logarithmically, we're going to use a suitable unit of measurement. We could use 1 degree of 12 EDO, though that's a relatively big interval, so let's instead divide it up into 100 equal parts. This is called a cent. Since 12 EDO divides the octave into 12 equal parts, and a cent divides 1 degree of 12 EDO into 100 equal parts, then that means 1 cent is equal to 1 degree of 1200 EDO, since there are 1200 cents in an octave. That means that 1 cent is equal to 2 to the power of 1 over 1200. 1 cent is so small an interval that you cannot differentiate between two notes that are 1 cent apart. Before we look at the revised table, let's see how we can convert EDO intervals and just intervals into cents. For EDO intervals, divide the number of degrees by the number of the EDO and multiply by 1200 cents. Here's an example. 9 degrees of 12 EDO is equal to 900 cents. For just intervals, take the base 2 logarithm of the interval and multiply by 1200 cents. For example, 5 over 3 is approximately equal to 884.359 cents. Let's go to the revised table now. In column 3, we can see the size of each just interval in cents, and in column 4, we can see the size of the closest respective intervals in 12 EDO, also measured in cents. Let's now subtract each value in column 3 from column 4 to find the differences. If the number is negative or blue, it means that the 12 EDO approximation is flat of the just interval, and if the number is positive or red, it means that the 12 EDO approximation is sharp of the just interval. It doesn't matter if the deviation is sharp or flat. What's important is that the closer the deviation is to 0, the better. We can see that 12 EDO approximates the majority of these just intervals decently. And 3 over 2 is very well approximated, with only about a 2 cent deviation. However, 3 of the approximations are further than 30 cents away, namely the ones for 7 over 6, 9 over 7, and 7 over 4. For this reason, it makes sense to ask what other EDOs can approximate such just intervals well, without getting crazy amounts of notes. There are several worth mentioning, but the smallest EDO bigger than 12 EDO that does a very good job at approximating just intervals is 19 EDO. Let's look at how well 19 EDO approximates these just intervals shown. We can see that unlike 12 EDO, 19 EDO approximates all of these intervals with different values. That's cool. What about the deviations? Let's see how the just intervals are approximated this time. Here, the biggest deviation is 7 over 4, with an error of 21.457 cents. So everything is within 30 cents this time. The smallest deviation, though, is only 0.148 cents. To put into perspective how good this approximation is, you wouldn't find an EDO that approximates this better until 232 EDO. And the first EDO to approximate 5 over 3 better than 19 EDO relative to its size is 422 EDO. Of course, though, these equal temperaments are huge and would be impractical, especially to implement them on instruments. And 19 EDO's approximation of 5 over 3 is so perfect that it's indistinguishable from an exact 5 to 3 interval anyway. If you want to learn more about 19 EDO, someone else has already made a short series on the tuning system. Be sure to check out the third link in the description for that. EDOs that approximate just intervals well for their size include 7, 10, 12, 19, 22, 31, 41, 46, 53, and 72 EDO. These are all worth trying out without having a crazy amount of notes. As mentioned previously, you can check the second link in the description if you're interested in why these specific EDOs do so well. Also, if you compress the octave by 3.9 cents, then 27 EDO is also a good choice, but I'll have to leave octave compression and non-octave tuning systems for part 2. There, we'll also learn about prime limits, MOS scales, and more.